Good afternoon, everyone, and welcome at this Tech at Lunch of the month of November. Today, I will talk to you about reversible bonding, debonding on command, circular bonding, all different terminology for, in fact, the same technology. And I hope to give you an answer at the end on the question, is it a fact or is it still a fantasy? So my name is Isabel van de Wijnberg. I'm project leader at Flanders Make, but this presentation wouldn't have been possible without the input of two of my colleagues, Ahmed and Jeroen, both European adhesive specialists. And today I will start with a little bit of background on reversible bonding. What is reversible bonding? Why should we apply it or why shouldn't we apply it? And I will also show you some examples, some applications, and I will give you some insights in ongoing research as well. So reversible bonding, what is it? First of all, we always assume that we have an adhesive joint which is intact. When there is no trigger active, the joint is still intact. We have a structural adhesive joint. At a certain moment, a trigger will become active and the components, the substrates, will come loose. Our bond is debonded. This can happen at the interface. It can happen in the adhesive layer. That's not really defined. But important is that the components, the substrates, will not be damaged during debonding. So we can rebond them if we would like to do it afterwards. And why would we apply reversible bonding? Well, it would make the repair of a product maybe a little bit more easy when you can decompose your product and repair the components. But it's also quite interesting if you can reuse some high value components. For example, at end of life of a product, there might be one or more components inside that are still have a high value and that you want to reassemble again, reuse again. But also during your production process, maybe there is a misalignment, a misassembly, and you want to reuse some of the components. And also don't forget at a real recycling at end of life, it's always good to upgrade your waste stream as much as possible. So if you can go to recycling of individual components, it's much more interesting to do so. So these are just some examples where we could apply reversible bonding. But there are challenges, of course, as well to reversible bonding. First of all, from a technical viewpoint, we should be sure that the performance of our adhesive is still good enough from a mechanical, physical, chemical point of view. And also that the trigger will not happen during the lifetime of your part. From an economical viewpoint, we have an extra cost for implementing this technology, and you have some equipment investments to do, but there will also be a switch cost involved. Your process will change, your adhesive recipe will change, and also really important, your business model. That's not always so clear. Sometimes there are split incentives. Your investment, for example, is done by a production company, but your return on investment, that's something for the recycling company. So this should be really cleared up front and analyzed very well. And also maybe environmental viewpoint. We always think it's much better to use reversible bonding, but is that the case? That's still a question mark, something interesting to be analyzed. So within reversible bonding, everything starts, of course, with a successful debonding. And how can we achieve debonding? Well, we identified three main categories. First of all, we have our mechanical way of working, which is quite straightforward, not so innovative. You just cut your sample or you tear them apart. If that will do the job for you, that's fine, but you have to be sure that your components will not be damaged, of course. Quite often your part will be a bit more complex, the situation will be a bit more complex, and then your thermal triggers might help. So you apply temperature to degrade your adhesive properties in such a way that you can debond your components easily. And you could also apply electrochemical triggers, for example, electricity or UV light to degrade the adhesive and to debond your components. That's still lower TRL research, smaller scale examples that are existing over there. Within Flanders Make, we mainly have expertise in the thermal technology. So this is really high TRL research, and we also work with thermal expandable particles, which I will explain on one of the following slides. So when we look at some real-life applications, some demonstrators, first of all, I want to explain a little bit the technologies that we will use. First of all, the induction technology. With an induction technology, we apply an electromagnetic field onto our components, onto our part. And if your substrate materials are not conductive, we can apply ferromagnetic particles to mix in our adhesive. And under an electromagnetic field, this adhesive will heat up in this way, will cure, so your bond becomes intact. It can also happen very fast. I will show this later on. And with the same way, we apply again an induction electromagnetic field. In the same way, we can reheat our samples in such a way that we reach the glass transition temperature and we can easily debond our parts again. Like I said, we can enable fast curing with this induction technology, which is of course a really nice extra. So it's not only about debonding, but also about fast bonding. What you see here on this graph, the vertical axis is a measure of the lab shear strength, which is also indicating the curing degree. And the blue bars are a commercial adhesive mixed with about 15% of these electromagnetic particles, ferromagnetic particles, and the green bars are mixed with 30% particles. On the left-hand side, you see a standard oven curing. So the parts need to be cured in an oven for 3 hours at 80 degrees, and you can achieve a similar strength with only 15 minutes in an induction under induction heating. So you can increase your speed from 3 hours to 15 minutes. And when we look at the debonding possibilities, this is now another sample than in the first graph. When we have a fully cured sample, well, if we put it in an induction field for only 2 minutes, you see that you can decrease the strength below 1 megapascal, and that's the strength with which you can just tear your parts apart with your bare hands. And also a nice possibility is that when you have the right surface conditions, you can also achieve clean debonding. So clean debonding means that you do not have to scrape off your adhesive residues after debonding. So that's what you see here at very well at the last sample. This makes it quite an interesting technology to apply in, for example, automotive batteries, construction sector, machine building, in every sector where your speed of production is important, of course, in combination with your debonding possibilities. And I have a short movie illustrating the fast curing possibilities here. What you see here is a robot that's handling a windshield, a car windshield. And on these windshields, nowadays sensors are being applied, for example, rain sensors. The robot is offering the windshield to a manual operator in this case, but this could also be another robot, of course, that will be applying the glue. So here is what you will see: manually application of the glue mixed with these ferromagnetic particles. And a nice thing of this example is that in real life, these windshields are quite often cured for several hours in a separate stock location. So you need to have enough surface to stock your windshields during production. With this technology, you will see that just within a couple of minutes, you can secure already your sensor. You can bond your sensor to your windshield and your production process will not be interrupted. So what you see here is a pancake-shaped coil that's hovering over the part that needs to be bonded. And after really a short time, we can put again the windshield in a straight position. So you see that you can fasten your production process very much. Another technology is the technology of the thermal expandable particles. These particles, they contain liquid hydrocarbon. At a certain temperature, this liquid will change into gas and the particle will really expand. And that's something that you see here on these photographs as well. If you mix these particles in your adhesive, you see what's happening. Your adhesive, it will start to swell and your adhesive will pull apart your adherents or will push apart your adherents and they will come loose. And in the next slide, you see here also a nice example. We have a spherical glass lens, which is mounted on an aluminum carrier ring. And when we put the complete part in an oven at 120 degrees for about 10 minutes, this is what's happening. We see the foaming of the adhesive. And I will stop the image now. You see the adhesive is really foamed up. It's pushing apart the parts, and it's really a brittle and really foamy substance, so you can just wipe it off with a cloth. So you don't have to scrape off your adhesive. It's not like it's really fixated to your substrates. It's easy to just clean and wipe off and then prepare the substrates again for rebonding if you want to. Now, we wanted to scale up these examples a bit, and therefore we went to an industrial automotive example. That can be, in this case, it's part of a bus chassis, but you could also apply it on a sidewall of a trailer or a train carriage, for example, everything where a metal chassis is bonded to a composite side panel. This was an exercise that we made together with the colleagues of Vito. We took the technical challenge, the colleagues of Vito took the economic and environmental analysis, and we got our materials from VDL Bus Company. In this particular example, we wanted to avoid production waste due to misassembly. You have huge panels that need to be bonded in a production process, and sometimes a misalignment occurs. If you want to debond your components, your composite panel gets quite often damaged. So this is something that we want to avoid by using this reversible bonding technology. First of all, from a technical point of view, of course, we start with a lab scale experiment, and we wanted to obtain debonding through induction heating, because the steel chassis is allowing us to use the induction heat in a very easy way. And we use some thermal expandable particles in the adhesive layer to make the debonding much easier and more rapid. We have to make sure that the temperature of 140 degrees is not exceeded, because otherwise the composite panel will start to degrade. And also the debonding time should be limited to a maximum of 15 minutes to avoid degradation of the composite panel. And we've seen that only with 5% of TEPs mixed in adhesive, we could reach a really nice result, which I will show you in the next video. And this 5% will also allow us to work with adhesive viscosity, which is almost normal compared to the normal recipe. So when we look at the example, what you see here is a cutout of the real composite panel. So it's about 2 meters wide. It's not a complete bus side panel. It's a cutout, and you see here 2 steel frames. Here you see the pancake coil that we use for our induction heating, and the black line here is the adhesive line. You see the induction coil moving. We are speeding it up a little bit, but in a total time of about 10-11 minutes, we will reach just spontaneous debonding. It's also, of course, due to gravity that you will see, voila, the panel will just drop down. So the heat is delivered through the steel chassis towards the adhesive bond line. So from a technical point of view, we managed to show the feasibility of this technology in this example. But what about economic and environmentally seen? Is it still also feasible and interesting to apply this technology? So if we just from a very logical way of thinking, we say, well, environmentally, we avoid primary production of a composite panel. So it's a positive story. And from an economic point of view, also there, we avoid an extra composite panel to be produced. We have an optimized production process. So also there, we expect some positive results. The colleagues of FIDO did a very complete analysis. I will show you just the conclusions in this presentation, but we've seen that the debonding process performs significantly better than just disposing a composite panel. But if you look at the total vehicle production, then the effect of this reversible bonding on the composite panel is negligible. There are much larger environmental effects, for example, the production of the motor, batteries being used, etc., etc. From an economical point of view, well, there were really important cost savings to be done. These cost savings, they were driven by the debonding equipment costs, of course, the value of the component that can be reused. So in this case, it's the composite panel, and also the frequency of the error that's occurring. Is it occurring quite a lot or just a few times? That will also be important for your economic story. So we've seen some really promising results for applying this technology in an automotive assembly, but you have to realize that these results are really highly case specific. So some key takeaways of all these examples. The high TRL technologies for debonding on command, they do exist. I demonstrated them. So we have seen some examples on the use of induction for fast heating to enable bonding and debonding. And we could also use particles in this process. Each application will require an optimized recipe for your adhesive, your particle content, your process conditions. So from a technical point of view, an optimization is needed, and also from a business point of view, it's really requiring a good and thorough analysis. Look at your environmental story, your economic story, and don't forget to inform and align with all your stakeholders involved within your company, but also externally. Otherwise, there might be some issues popping up when it's already a bit too late. But from my part, I think this reversible bonding technology, it's really a fact. It's not a fantasy. We can already apply it in a high TRL example. So it's ready to be implemented for sure. Further ongoing things, public research that's ongoing within Flanders Make. We are active in a project on the use of nanoparticles in polymers and in adhesives, which might optimize our performance of our adhesives as well. We are also active into European projects, one on the use of biodegradable debondable adhesives and one on the use of smart and digital tools, for example, also on debonding and command. So if you're interested in one of these topics, please feel free to reach out to us and we will be happy to inform you on these projects. But also, if you are inspired with the things that I just told you and you are already using adhesive bonding and you want some support in checking if reversible bonding might be something for your company, or you want to have some optimization done with your process, with your product, again, reach out to us. We will be really happy to assist you in this. And if you're not making a use yet of adhesive bonding and you think you want to switch your joining technology, also there we can certainly support you in this process as well. So please, I will be happy to give you more information on our research on the things that we can support you with. And if you have more questions on the things that I just presented, please let us know. Thank you for your attention.